Hi, I'm Kristin Schild. I'm an assistant professor at the University of Maine in the School of Earth and Climate Sciences and the Climate Change Institute. I broadly look at the ice and ocean interactions, or ice-water interactions. So I study glacier hydrology, how tidewater glaciers interact with the ocean, and then also icebergs, as after they detach from the glaciers, how they melt, how they change and move, and also impact their surroundings. My background is in physics and math, and I've been looking at these types of tidewater glaciers for about the last 15 years. Something that really excites me about this work is that we have so many questions that we can ask about this system. So not only how are these glaciers changing and responding to differences in climate, but also what happens after the ice leaves the continent and enters the ocean. To try to better understand this system, we need to combine all sorts of different disciplines and expertise, not just glaciologists like myself, but geophysicists and oceanographers. I get to work with all of these different people and learn from them and try to figure out what is going on with these glaciers. So as water passes through a glacier, it can impact how the glacier behaves, and that's a lot of what I really enjoy studying. As climate continues to warm and as we get melting during the summer, that meltwater needs to go someplace. It melts the surface of the glacier. It can then flow into crevasses, into depressions, and water always wins, and so it will go into cracks in the glacier. It can fracture all the way down to that glacier bedrock interface. There's not an end point to when this meltwater contributes to the demise or the stability of a tidewater glacier. One of the big challenges in studying icebergs is that they're so dynamic, but so much of their movement, their melt, their deterioration is based upon their geometry. And about 90% of that iceberg is underwater, so we can't tell what the shape is or how deep it goes in the water column. And so one of the methods that I got to be a part of developing was to capture these icebergs in 3 dimensions. And so we flew drones over the top of the iceberg to create a surface 3-dimensional model. And then we also put multi-beam sonar in the water and tilted it towards the iceberg and did a few passes with the ship in order to create a 3D subsurface of these icebergs. And the really challenging part is that as we are surveying them, they are actively moving, they're deteriorating, they're tipping, they're breaking apart. And so in order to combine our drone surveys and our multi-beam surveys, there needed to be a lot of post-processing that was done. And we actually used GPS units that we deployed by helicopter on top of these icebergs in order to fully reconstruct them. So these were some of the really fun, unique data sets that I got to combine together in order to capture 3-dimensional iceberg geometries. I think one of the most impactful experiences I've had as a glaciologist was during one of my very first field seasons out to Greenland. Prior to that trip, I had really studied these glaciers only through remote sensing imagery, so just looking at satellite images. Once I set foot on ground, one of the biggest surprises to me was the scale of these glaciers. Even though I had seen them day in and day out, I knew exactly what the geometry of them would be, where the position would be. Seeing the scale in real time, how big they are, how large these crevasses are, how strong the calving events are, and how loud they are, it gives a completely different experience and understanding of the power of these glaciers. When I'm teaching my glaciology course, one of the fundamental concepts that I really hope that my students walk away from my course understanding is the idea of mass balance. What comes in, what goes out, how we can calculate mass balance. And one of the really important things for me when I'm teaching my glaciology course is being able to incorporate not only my field experiences, but show students exactly how we collect data. And so often I teach this course in spring in Maine. So it starts in January and February. So we go out and we dig snow pits. We use all of the tools that we do when we are out in the field. I have them designing some of their own projects to collect real samples and evaluate a snowy environment. So I like to bring my field work into the classroom, but I like to bring it in after they've had a chance to be hands-on with that equipment, so they can learn how it works and then learn how we also use it in very remote places. I find the field of glaciology incredibly exciting and incredibly interesting. However, in order to really get at a deep understanding of these systems, we cannot do our science in a vacuum. We need collaborators, we need collaboration, we need diversity in the way that we think, the way that we approach problems and questions. And the only way to do that is if we are part of a collaboration, we are part of different networks, we are able to have these conversations with other scientists that are outside of our disciplines and outside of even the physical sciences. Have these conversations with communities, community partners, in order to understand how our system has much, much broader impact than we've even been able to consider. And so having those communities and those networks is fundamental to being able to successfully answer these questions or address real concerns within our communities. I am also a member of the New England Arctic Network and am the coordinator for the UMaine Arctic Initiative. And both of these networks are designed to bring together people across campus and across the New England region that are interested in the Arctic in any sort of capacity, whether it's policy, law, social science, physical science, to start to develop these conversations about our shared interests and also our shared strengths and our different strengths that we can pull together in order to try to address some of these challenges that we're facing in the Arctic.